For my experiment, I had 5 configurations. A couple of standard configurations, standard in that it's the configurations that are the way globe deniers have been doing it most of the time, and 3 variations to bring additional data. I'm showing the layout in the daylight here because the night shots are kind of hard to see. So what I had were these 2 outdoor chairs with cushions, as you will later see, facing into the moonlight. One chair is positioned under the umbrella while the other is off to the side in full view of the moon with nothing overhead. I also had a table set up which was in full view of the moon, and I made use of some plywood and cardboard boxes to block the moonlight. Now, in addition to the infrared thermometer, I purchased a set of 5 classic thermometers. Their uniform manufacture means that they are made of the same materials, have the same level of reflectivity, and thus should be reliable surfaces to sample with the infrared thermometer, in addition to the fact that they will tell us their temperature at all times. After leaving them all out in the moonlight together for a few hours, they all read 47 degrees. A chilly night by California standards, with the thermometer labeled C being a hair higher, but not to the point of being 48 degrees. Now let's see what happened. The samples in configuration 1 were matching thermometers, matching thinking is critical t-shirts, and matching seat cushions. The thermometer in the moonlight, thermometer A, read 42 degrees. The shirt in the light was 47.6, give or take. The cushion was 47.2 and a bit lower. And the thermometer A surface was 46.6. Thermometer B under the canopy was 44 degrees. The shirt was 49.6, the cushion 48.8, and the thermometer surface 48.6 and a little less. Let me put all that up at once. Doing the math, the objects in the moonlight were 1.9 degrees cooler on the average. Does this mean that moonlight is cooling? Well, one way to tell is if I tried it again, but without the moon involved. So I waited a few days so the moon would appear later and later until I had a night with no moon in the sky. I tried it again. It's a similar setup, except this time there's no moon above. The one chair is under the canopy and the other chair is under the open sky. The one chair is under the canopy and the other chair is under the open sky. The open air thermometer reads just under 39 degrees. The shirt, 41.7. This wood is 41.9, but I won't put that into the average because it wasn't in the first batch. The thermometer surface is 40.5, and the cushion is 36.4. Under the canopy, the thermometer reads 40 degrees. The shirt is 43.2, the wood 42.3, the thermometer surface is at 41.7, and the cushion is 39.5, for an average difference of 1.7 degrees cooler in the open air. And that's with me calling the open air thermometer 39 degrees when I know it's a bit lower. In other words, the results are the same, moon or no moon. An object under the open sky cools faster than an object under cover. The moonlight is not cooling. The sky is. You see, the open sky is cool and all objects radiate heat. An object in the open sky radiates its heat relatively freely and cools down, while an object under a blocked sky radiates its heat as much as it can, but it also receives heat from the object blocking the sky, and thus it cools at a slower rate. It's called radiative cooling. Look it up. To test this, I came up with a few more scenarios on that first night with the moon, which I will go through quickly, so this isn't too long. I set up these objects on this table with this board blocking the moonlight for one set of the objects. Here's the data from that. Then I took a similar board and leaned it over the open sky object, making sure to be at an angle that didn't block the moonlight. And then I left them for another 30 minutes. And even though this set is still in the moonlight, it is no cooler, because it has heat radiating objects near it, just like the other set. I made one more variation to the original canopy setup that first night under the moon. Leaving everything where it was, I took large sections of plywood, about half the area of the overhead canopy, and set them next to the objects that were in the open moonlight. I came back 30 minutes later, and lo and behold, the temperature difference disappeared as the moonlit set received radiating heat from the wood, just as the other set did from the overhead canopy. The moonlight was not cooling.
My body started shaking and I can't take no more. No, no. No, I just want to get close to you and taste your love so sweet. And I just want to make love to you. Feel your body in the still of the night.
Recording? Yep. Okay. See, the moon's right over there. It's full as heck right now. You can zoom in on that. And we're gonna test temperatures on one side of a car to another side of a car. We're gonna do it on two different cars. And the wind isn't even a factor right now. It's not even blowing. Are you still recording?
Yeah.
Okay, come on. So this is a thermometer, and it's reading 59 degrees. This is the moonlight. We'll get out of the way of the moonlight. 62 degrees, and this is in the moonlight.
Hold on.
60, wow, 60 degrees.
Okay, I gotta keep it right here to see it.
59 degrees. Now we're going to move over to the other side of the car where the moon is not on. We're just moving. And we're going to try this again here. It's now reading 65 degrees.
Okay, now just move the laser up.
And I'm moving the laser to where the moonlight is shining, and it rapidly drops.
Okay, move it back down.
I'm going to move it back down here. Goes back up.
Jump back up.
65 degrees, and back on the hood where the moon is shining. It's almost a 10-degree change. And we're going to do this on another car over here. We're going to go out of the moonlight. It's a dark car.
Moon's there.
It's a dark car. This is out of the moonlight, 66.6 degrees. We're going to move it into the moonlight slowly. And it's dropping dramatically. Same kind of paint on both the hood, or the trunk, and the side of the car. 55.8 in the moonlight. Moving back to the side. Jumps up to 66 degrees.
Yep.
That's proof that the moon is a cooling influence to us.
Cooling light.
It's a cooling light, not a heat light. 55 degrees in the moonlight. 65 degrees out of the moonlight.
10-degree difference.
10-degree difference.
Do next car here.
Another car, we got silver paint. We had white paint, now we had darker paint, now we have silver paint. And here we go again. You can see it, folks.
Let me see if I can get the moon in there when you're doing it. Okay, the moon's right
Can
there.
you see it?
So this side of the car is out of the moonlight.
Can you see it?
Yep, 65.
And then we're going to move it up on top of the hood. It goes down to 58 degrees. 50. Oh,
You're moving it.
there we go. Silver paint. 59 degrees. 58 degrees in the moonlight.
Yep.
Now we're moving in the out of the moonlight. 64, 65 degrees. The moon is a cooling light.
Yeah.
Proof right here, guys. 63 degrees out of the moonlight.
Yeah.
58 degrees in the moonlight.
Yep.
56.
One more time, bring it back
Bring
down.
it back down again, out of the moonlight.
Yep.
That's proof. Proof that the moon is a cooling light. Thanks for tuning in tonight. Have a good one.
Okay, so we have a full moon out tonight, and I'm testing the moonlight and the shade, but in this case I'm going to be focusing that light through a Fresnel lens, and I've taped it to a cardboard piece so that I can have the light focused on a cookie sheet here. And as you can see, the light of the moon is shining on the pan, and the cardboard keeps from any heat, or I should say, yeah, from the heat going up to the sky, radiating out. And basically containing the situation here. So I'm going to go ahead and try this. I'm going to try to turn my light off here. Alright, so I have my light off, and I've got the Fresnel lens focusing the moonlight of the full moon on a clear night. I have this isolated with the cardboard so that we can look at this clearly. I'm going to get my thermometer very close, IR thermometer, very close to the spot. And then I'm just going to move it around the pan to see what we get here. Alright, so we have 57.9, 56, 56.6. Immediately when I move away, it seems to go up. 58.2. Let's see. Try to focus on both here. So I'm focusing on my little spot. 56.8. Move away from it. It jumps up to 57. Let's see, let's go back. Just focusing on that little focused moonlight on the pan. 56.8. We move away. Not a lot, but seems like it is cooler. 56.8. Now we jump up to 57. Alright, so that's about a degree. Get back on that spot, 56.8. And then we move down the pan and it jumps up to 58. Trying different spots on the pan. Back to our spot. Yeah, 56.8 when I get it right on that little spot. And then back to 58.
Alright, so this is focused moonlight across a 31 by 26 Fresnel lens. You can't really see. That's the moon coming through the lens. I'll show you in the day later. Focus to a single point. Here we go with the numbers while I get this lined up. So on the edge where the light is, and it's 55 degrees-ish. I go to the light. It hits. Then I have 51.9, 51.6, 51. In the light, you can see the lasers hitting the light. When you go off target, it goes back up to 55 degrees. So there's some deflection there between in it and out of it. Here, I'll move it like that, make everybody angry. 52, 53. It's cooling up the dish. Cooling to the center. Back to the focus moonlight point. 51 degrees. Across the way. Starts to warm up again. 4, 3. Back to where it's been swinging across since the moon's moving. Back to the point of moonlight. See, 51 degrees. So, I think I've determined that the moonlight is cold, but it ain't cold, that cold. I mean, you take a Fresnel lens and focus it onto a single point, you're going to get a difference. Not maybe, what, 5 degrees? The sun gives you about 500 degrees difference. The moon gives you about 5 degrees difference, as you can see. But yeah, this is all with the Fresnel, which I'll show you in another video. There's the back of it. There's the moon, almost full. I think it's a little sliver of not full. I know it's boring, but I think there's your result though. It's consistently cooler in the moonlight.
Not even sure if you can see that, but right here in the, because it's so dark out. Let me see, can I even turn a light on here? Yeah, I don't think I have a light, but if I point over here in the shadow, it's a little bit warmer. It's 18 degrees over there. And then you can see I can just drag that laser over to where it's in the direct moonlight. And it's 13. Right here back in the shadow. It's going to be 19. And as soon as you take it back into the moonlight, it's 14 again. And you can do this over and over. 51. In the light. You can see the lasers hitting the light. When you go off target, it goes back up to 55 degrees. So there's some deflection there between in it and out of it. Here, I'll move it like that, make everybody angry. 52, 53. It's cooling up the dish. Cooling from the center. Back to the focus moonlight point.
But what if it was? What if there was a heretofore unknown natural form of light that cooled objects? Would that mean that the moon couldn't be reflecting sunlight? Is there a property or law of physics that says cooling light must be self-generated? Do we have examples of natural objects generating cooling light? No.
Heated objects glow, and the heat motion energy of atoms and molecules becomes the radiated light energy. Along with such thermal radiation, bodies can also emit light by converting other types of energy into the light energy. Such cold light notions are altogether called luminescence. Luminescence is the emission of light caused by the excessive radiation of the body under the given temperature and lasting significantly longer in the light wave period. Depending on the energy source causing this emission of light, there is chemoluminescence, emission of light caused by exposure to chemicals, electroluminescence, caused by an electric field, and photoluminescence, caused by light. According to the period of luminescence, there is fluorescence, short emission of light, and phosphorescence, long emission of light. Just like any other kind of radiation, luminescence is characterized by a spectrum, radiant flux spectrum concentration, and by polarization mode. Along with such general characteristics, there are also some that are specifically applied to luminescence. The intensity of luminescence is rarely interested in itself. Instead, we use a notion called luminescence efficiency that describes the ratio of radiated energy to the absorbed energy. Initially, the notion of luminescence was applied to visible light only, but today it also refers to the radiation in the infrared, visible, ultraviolet, and X-ray ranges. Luminescence is used in production of fluorescent paint and other phosphorus-based compounds for application on scales of devices designed for use in the dark. Many forms of natural luminescence were known a long time ago. For example, glowing of insects, fireflies, sea fishes, and plankton, as well as the aurora. Today, such natural luminescent effects have been supplemented by multiple artificial ones. Solids and liquids that are capable of luminescing are called luminophores. In household devices, luminescence is primarily used in luminescent daylight lamps and cathode ray tubes of kinescopes.
first is that a given type of atom will only absorb light of a certain fairly precise set of frequencies called atomic resonances. In a nutshell, the reason for this is because an atom can only absorb light if it can use the energy of that light to transition from one state to an excited higher energy state. And due to quantum physics, the energies of these sorts of transitions are generally discrete, meaning it's kind of like Goldilocks. If the frequency of light is too high or too low relative to one of these resonances, the atom won't absorb its energy because it has nowhere to put it. The second potential issue here is atomic re-emission. If an atom absorbs some resonant light, it is pushed by it and its momentum is changed. That's what we want. However, as we said, the energy of that light has gone into changing the states of the atom from one energy state to a higher excited energy state. However, the thing with excited states in quantum mechanics is that they are not stable. After a certain amount of time, based on what's called the excited state lifetime, the atom will give back that energy by re-emitting new lights and fall back to its ground state. So at first glance, it might seem that this whole idea cannot work. An atom absorbs light and as a result gets a little push, but then it re-emits that light a bit later and is recoiled or pushed back by that emission. So the net push would seem to be zero with nothing really being accomplished. But actually, that's not the case. That would be the case if the atom was absorbing light from all directions. But when an atom re-emits the light, it does so isotropically, or omnidirectionally. In other words, it emits in all directions equally. So that's maybe a little subtle, but the point is, in our little setup, absorption is only happening in one direction, but re-emission is happening in all directions. So absorption does indeed result in a net push, but re-emission doesn't, and that doesn't undo things. Finally, the last bit of stickiness we have to understand is what is called the Doppler effect. The Doppler effect is what is happening when you hear a police or ambulance siren, and as the car is heading towards you, the siren sounds higher pitched. But after it passes you and starts speeding away from you, its pitch then shifts to a lower frequency. That's the Doppler effect. This is a general phenomenon that happens with all wavy things, including light, where basically, if I have a source of waves emitting with a certain frequency, the frequency you receive as a receiver of those waves will be upshifted if you have a velocity towards the source, or downshifted if you have a velocity away from it. Now, let's think about what this means for our atoms and a laser. Let's say I have a laser that outputs green light. By saying it's green, I'm saying it has a certain frequency. And let's say I have an atom that has an atomic resonance corresponding to red light. Well, if the atom is stationary, it won't absorb the laser. It's too high frequency. However, what if the same atom was moving away from the laser? Well, because of the Doppler shift, it now receives that light as a lower frequency. We say it is redshifted. Well, now it actually can absorb the light, and it does. This, by the way, is also one of the main reasons for this broadening of energy levels that high temperature causes that we talked about previously. A gas of hot atoms, as we discussed, has a distribution of speed and direction. So if I shine a laser that is off resonance for a stationary atom, there may still be atoms in the gas that see it appropriately red or blue shifted, such that for them it is resonant and they absorb it. We call this Doppler broadening. But okay, enough with the fundamentals. Our key concepts were that light can push atoms if the atoms can absorb that light, that atoms can only absorb certain frequencies, and that the frequency of light an atom sees in terms of whether it can absorb or not actually depends on its own motion relative to the laser source. So with that understanding, let's finally get on with our main discussion. How do we actually cool atoms down? Well, historically, the first starting place was by trying to cool atomic beams. Now, the term atomic beam probably sounds both like we're accelerating atoms to make them go really, really fast, which, is the opposite of our goal, and also probably sounds like a super fancy device like some enormous particle accelerator or something. But actually no, on both accounts. To make an atomic beam, one basically just takes a gas in a box and just pokes a hole in the side, like popping a hole in a tire. Now, why would we choose to cool these beams rather than just a gas? Well, because as we said, if the light is heading in the opposite direction to an atom and that atom absorbs it, the atom is slowed. However, in a gas of atoms, some atoms are heading towards the source, but others are heading away from it. And if an atom moving away from the source absorbs light, then it's actually accelerated by it. It gets a kick in the pants and goes faster, which is the opposite of what we want to do. So given that, atomic beams are a simple and easy solution. And that's why, historically, this was the first step we took towards cooling with light. Pioneered by people like William D. Phillips, who won a Nobel Prize for this work in 1997, and Arthur Ashkin, who we've actually already talked about him and his 2018 Nobel Prize in an earlier video. And it works, a little bit. If you have an atomic beam whose atoms have a distribution like this, with a certain average speed or temperature, after the beam is done with it, it'll look something like this. And this distribution has, on average, a slower speed. The atoms are cooler. But looking at this, you can maybe see the problem. Only the atoms in a certain narrow range of velocities are being cooled down. And the reason for this is because of the Doppler effect. We said we'd pick the frequency of the laser to match a certain atomic resonance, but that resonance gets Doppler shifted by the motion of the atoms. And so if it was resonant when they were going fast, as they slow, they see the light as red shifted, and then it's no longer resonant. And that is what we're seeing here. So how do we stop that? Well, people came up with two very clever ways of attacking the problem. To reiterate, the issue we have is that as the atoms beam out and absorb the incoming light and are slowed down, their resonance and the light's frequency are Doppler shifted such that they then become off resonant. So the two clever ways is to, in real time, as the atoms are flying across the experimental apparatus, somehow either shift the frequency of the laser or somehow shift the resonances of the atoms. One or the other is altered in real time to keep the resonance going in step with the Doppler shifting. The first of these approaches is called chirp cooling. We've seen this word chirp in a previous video about the 2018 Nobel Prize, and it just means a wave whose frequency is actively changing in time. And that's what we want to do. As the atoms are slowed by absorption, we want to actively detune or chirp the frequency of the laser to restore resonant absorption. The second of these approaches is called Zeeman cooling. Well, actually, if you want to Google and learn more or something about this, it's actually more often called Zeeman slowing. At the heart of this Zeeman cooling is an important effect of quantum physics called the Zeeman effect. In a nutshell, it is a prediction of quantum mechanics that if I have an atom with certain energy levels and I place it in a magnetic field, there will be a shifting of these levels in energy. And in fact, the stronger the magnetic field, the stronger the shift. And this is just what we need. We want to actively shift the atoms' resonant energies in flight. So specifically what we do is we put the entire apparatus in a magnetic solenoid that generates a magnetic field. And we make it so that the strength of that magnetic field decreases along the length of the apparatus. Like literally as the physical distance from the atomic beam increases, we have magnets with less and less coiling, what's called a tapered solenoid. And that's basically the idea behind chirp and Zeeman cooling. Either you actively tune the laser or you actively tune the atomic resonances in flight. With these easy to dream up but hard to implement ideas, you could take a distribution of speeds like this and bring it to this. And by 1985, such approaches were cooling atomic beams down to temperatures of around 1/10 of 1 degree above absolute zero, and about 25 times colder than the original atomic beams. But things didn't stop there, because once you've gotten your atoms slowed down that much, there's actually an opportunity to trap them and cool them further through the final technique we're going to talk about today, which is Doppler cooling. The reason Doppler cooling is called that is because unlike the other techniques where the Doppler effect was our enemy, we're constantly fighting against it, in this technique we can finally make it work for us. To see how, forget about our typical setup of atomic beams and consider a gas of very cold atoms that have been pre-cooled by some other technique, and that is pinned between 6 lasers, 2 opposing lasers for each axis. Now, remember, we're talking about a gas now and not a beam, so the atoms aren't all moving in the same direction and the direction of their motion is random. And the trick is that we take our lasers and get their frequency to one that is just below a resonance of the system. We so-called detune the laser to an off-resonant lower frequency. As a result of this, we'll see, because of the Doppler effect, not only will these atoms start cooling down, but they'll effectively be trapped in place. To see why, let's just think about one axis. So I have 2 opposing lasers, and in their center I have this gas of atoms, and they're detuned to a frequency lower than an atomic frequency for a stationary atom. Now, there's a distribution of speeds and directions of these atoms, but let's look at one moving to the right. Well, because he's moving to the right, it's moving away from the left-hand laser, and thus it sees it as redshifted to an even lower frequency. And so it's even more detuned, and as a result, it'll never absorb it. And that's good. If it did, it'd get a shove in the back and would get a speed increase. However, what about the right-hand laser? Well, it's heading towards that laser, and as a result, it sees it as blue shifted. And bam! Look, it's now on resonance and is absorbed, and the atom gets a kick backwards. So you see how this is working. If it's stationary, it doesn't absorb because the lasers are off resonance. If it's not stationary, the laser in the direction, shining in the direction of its motion, which could potentially give it an unwanted speed boost, is now pushed even more off resonance because of Doppler shift. Where the laser shining opposing its motion, is Doppler shifted into resonance, and it is pushed back to a lower speed. And voila, Doppler cooling. Using this method, you can get to temperatures of about a few hundred millionths of a degree, or about 250 times colder than the limits of Zeeman cooling. Furthermore, what makes Doppler cooling different from the others is that it is also a trap of atoms. This trapping is often called optical molasses, and that's because it's not really an atomic trap in the usual sense, where the atoms are being held by an attractive force, usually through some magnetic or electric field, towards the center of the trap. Rather, the atoms are trapped because their direction of motion is constantly being scrambled and their speed constantly stolen. They're not pulled, but anytime they try and get anywhere, they're randomly knocked in some new direction, and instead, thus, they are forced to perform a so-called random walk. And it's this random walking that is largely holding them in the center of the laser beam. Also, by the way, a bit of flavor, one of the big people to first demonstrate optical molasses was Stephen Chu, who because of this work shared the 1997 Nobel Prize with William D. Phillips, who we talked about earlier, as well as with Cloud Cohen-Tanuji, whose contributions we may talk about in a later video. Stephen Chu would later then become Secretary of Energy for the Obama administration. So the guy is a Nobel Prize winning physicist and former US cabinet member. I've done nothing with my life. Well, on that note, let's wrap things up. These techniques are not actually our current limit for cooling with light. There are so-called sub-Doppler techniques. In fact, Stephen Chu and his group themselves accidentally discovered sub-Doppler cooling while trying to originally demonstrate Doppler cooling. But maybe such techniques are better as a story for another time. So, in this video, we learned about how to use light to cool things down, about how light's momentum can be used to push a speeding atom and slow it, and about how the Doppler effect can work against such attempts. We also learned about how these issues can be addressed by either actively changing the frequency of the laser in flight, which is called chirp cooling, or by actively modifying the resonances of the atoms using magnetic fields, which is called Zeeman slowing. And finally, we learned about how one can use multiple counter-propagating lasers that are detuned to a resonance to both trap and cool a gas of atoms, which we call Doppler cooling. Alright everyone, please like and subscribe to the channel if you like this stuff, and have a good one.
Good morning everyone, Brian here. It's about 4:30 a.m., just after actually here in Florida. I've been up for about the past 2 hours thinking about this. My mind is racing with this new idea about moonlight and possible capacitance of the moon. Is capacitance a word? I don't know, but I think it is. But yeah, my mind is racing. I'm just gonna have to go until I faceplant because I can't stop thinking about this. It's too amazing. People have made great comments both on Facebook and YouTube about this topic. Awesome suggestions. What I want to talk about is the cynic made a comment on YouTube about deserts and temperature swing, and how in the desert in the daytime it just gets very hot, well over 100 degrees Fahrenheit, and then at night it gets very, very cold, like down to freezing temperatures. And I was thinking about why that is, and I remember, and the reason's got to be because there's no moisture, there's no water out there, because water holds heat very well. Is another thing my dad ingrained in my head as a kid is that's why you see fog above ponds when the air temperature drops very quickly, because the water retains the heat that it had. And if you live near the coast, in the springtime it takes a while for the water to get warm as you get into the summer months, and then as you go into the fall months, when the air starts to get cold, the water's still warm because it holds onto the heat. So it also takes longer for water to heat up. Water is a very good insulator, so to say. And so I was thinking about this, and somebody else posted under, I can't remember who it was, made a comment about heat escaping from the desert. Is it really black body radiation going out into space? And I was thinking about that. Well, yeah, because the heat's got to go somewhere, right? Where's the heat going? Really, it's got to go somewhere. It can't just go out to colder areas of Earth, because they're also cooling down too. So it's got to go up into space. That's what I've always thought. But then I realized, thinking about this, laying in bed, well, there's kind of a problem that there's a thermosphere in the way that's about, I don't know, at least 400 kilometers thick with very high temperatures. That's an issue there. Do you agree? How's the heat going to radiate up from the desert through this? Hot goes to cold. It's definitely not. We're kind of insulated against space at that point. That's what holds heat into Earth. So where's the heat going? It's got to go somewhere. I don't know. A little more evidence. Still, we need to prove this. But another thing I was thinking about is, what is a capacitor? Actually, what is it? And also, Ank, backing up, Ank came in again. Anky, you gotta tell me how to say your name, but with another great point about capacitors. And I had to look this up. I had to wake up and look this up too. Apparently, capacitors, they don't charge evenly. The rate of charge and discharge varies, and that's exactly what the moon phases do. He pointed out that if you look at a moon calendar, he actually posted a link in the comment to the moon calendar, which is so interesting. When the light first starts to appear, as you get that little sliver as you're heading towards the waxing crescent or the waning, I get them mixed up, but it's basically you get like 1% of light, and then 5%, and then 12%. This is going up in consecutive days. It's not a uniform linear is the word I'm looking for. Opening of the light, or the light appearing on the moon. It kind of jumps up and then jumps down. It's like it's almost maybe exponential. I'd have to look at it more, but it's not linear, and supposedly that's what capacitors do too. So this is really interesting. But I got my circuits book out, basic circuits book. I held on to this one too, just to read the definition of a capacitor. It says, a capacitor is a circuit element that consists of two conducting surfaces separated by a non-conducting or dielectric material. A simplified capacitor and its electrical, it's just describing the figure, but there are many types of capacitors, and they're all categorized by type of dielectric material used between the conducting plates. So what I'm thinking about is what are the sun and the moon the plates, and then there's some kind of dielectric material between them, or is the moon the dielectric material? This is just something to think about. It's basically like an insulated material, something that doesn't conduct. And so just throwing that idea out there, get more people thinking, because as I've said before, we're all working together here. So many people have good ideas, and then and I can be the guinea pig on camera, just reading all these ideas, trying to put them together, and then throwing them back out there, and getting more people's input on this, and we can keep going and charging towards truth with all this stuff. And on Facebook, I think Stefan Ludwig made a comment about lenses with moonlight. You know, when with sunlight you can take a magnifying glass and you know, you can set a piece of paper on fire if you focus the sunlight. I used to do this when I was a kid. I think every kid has done this. You know, kids burn ants and stuff. You know, boys just doing mischievous things. I don't think I ever burned ants though. But so what happens if you do that with moonlight? Has anybody ever tried that? And immediately I thought, well, what if you did that on a candle flame? So I tried to draw this as a really crappy lens. This could be a magnifying glass or some type of lens. What if you know, I guess if the light is actually traveling up, if it's pulling light away from the flame, I mean, really we can't see which way the light's moving because it moves too fast, but you're still focusing the light. Would it actually intensify the flame? Is this the way we could actually see the flame intensify over another flame that's covered from moonlight? Or even if they're both exposed to moonlight and you use a lens on one, this is another thing I really want to try. I'm going to have to get a good magnifying glass to do this. And I think there was another point I wanted to make. So many thoughts. I could probably ramble for hours in front of the camera here, but I don't want to waste too much of everybody's time. What was the other thing? Oh yeah, I want to point out that we're not measuring the temperature of the light. I said that in the first episode because I was too excited. I mean, it is semantics, but we're measuring the temperature of the air. Just like, you know, I explained in the Balls Up Physics episode 4, is the thermometer measures the kinetic energy of the substance. So we can't directly measure the temperature of the light. So just keep that in mind. I'll probably say that again when I'm talking quickly. We're measuring the temperature of the air, so the moonlight is actually cooling down the air as opposed to the sun. You know, it's definitely true that if you measure the temperature of air in direct sunlight, it's gonna be warmer than the temperature of air in the shade. So what we're looking for is it the exact opposite with moonlight. And so I've also been looking at FLIR FLIR infrared cameras too, because I really want to do this right, and there's some deals out there on Amazon. So if anybody's got one of those and they want to use this and try to position it on a line between moonlight and shade and just record the results somehow, that would be great. Because the more we can show the moonlight cools the air or cools whatever it's shining on, the better. And then one more. Somebody else made a comment about how clouds look around the moon, you know, and sometimes you see those really cloudy nights. It looks like sometimes it looks like the moon, there's like a hole in the clouds, you know, like I see this a lot. I mean, especially since I've been studying flat earth theory, I've been watching the moon on cloudy nights, and people talk about how it looks like clouds go behind the moon. Well, what if it's absorbing energy from the clouds? You know, H2O, I mean, clouds are basically water. There's a lot of energy in hydrogen. You know, H2 gas, hydrogen gas, there's an extreme amount of energy. I mean, that's what happened to the Hindenburg. You know, it's filled with hydrogen and it blew up. That's why we fill pumps with helium now. And so, you know, these are things to think about. I'm speculating, yes, of course. I mean, basically I'm saying the moon is eating clouds, so I mean that's out there. But it's just things to think about, more ideas to throw out there. The more ideas we can get together and keep working together and charging towards truth. I keep saying that, it's getting corny, but yeah, just want to record some ideas. Can't sleep, so hopefully I can fall asleep sometime this weekend. But I hope everyone out there is having a good time with this, has as much fun as I am. So I'll talk to everybody soon. All right, peace.
So even if the light from the moon was cooling, which it is not,
Hold in the center. Back to focus moonlight point.
it could still be reflecting sunlight, which it is. Don't believe me? Well, there's a simple test we can do, and it's one of the reasons it took me so long to get this video out. I had to wait until the right conditions, a clear day when the sun and the moon could be seen in the same sky, which I was able to find on Saturday, December 1st. This simple test will show not only that the sun is the light source on the moon, but also that the sun and moon are not local objects, but are quite distant. All you need is the sun and the moon in the sky and something like this ball in the foreground. The geometry is simple. If the sun and moon are local, then at this moment, the sun and moon are closer to each other than they are to this ball, and thus the angle of sunlight hitting this ball will be drastically different from the sunlight striking the moon. But if the sun really is as far away as science claims, this ball and the moon are essentially the same distance away from the sun, and the light striking them will be at the same angle. This ball and the moon will show the same phase. This has been done before. It's nothing new, yet it is constantly being ignored by the globe-denying crowd, so I'm doing it here again. There's the moon. I have the ball in the foreground. I just need to move into a position where I can capture the moon and the ball from the same angle, because my position relative to the ball affects how its phase appears to me. There's the moon, and here's the ball. This ball only has one direct light source, the sun, and its phase matches that of the moon, because the moon has only one direct light source, the sun.
The other night I was sitting on the back porch having some coffee and looked out the window, and the moon was headed down toward the horizon, and I could see it was way off from what it should be to line up with the sun, which had already set. So I called my wife and I said, "Hey, come here, I want to show you something." And so she came out and took a look. I said, "What's wrong with the angle of that moon?" And she said, "Well, the sun has gone down beyond the horizon, right below the moon there." And I said, "No, it hasn't." I said,
In the summertime, it sets right there. I said, but in the wintertime, it sets southwest. So that's way off. And she said, oh, you're right. So I went in and grabbed my Nikon P1000 and took this photograph that you see here and the video that you saw before that. And that was on January 13th of 2019. The next day I went out to the Cape Argo lookout and used my theodolite app for my iPhone and got some readings for the sun set and for the moon. With those readings in hand, I'll try to give you a better perspective of how far apart the sun and the moon were. The sun was at south 64 west and the moon was at north 89 west. So essentially we have the sun southwest and the moon was due west. So now I want to show you what bothered me when I was sitting there looking out of my window drinking my coffee. Look at this moon and look at the angle to the sun. It doesn't work out very well. In this visual representation of the angle of the moon and the sun, I clipped the moon right out of the video that I took of it, so the angle is right. Of course, this is just a visual representation, so you can get the idea of what I'm talking about. A lot of people don't realize that the moon rotates back and forth, and like a clockwise and counterclockwise. And when it rotates, the moon, the shadow, and the highlighted side all move simultaneously. And, you know, that's why we see such wild angle discrepancies between the moon and the sun. And this happens on a daily basis. Throughout the day, in one day, if you have a clear sky, you'll see the moon do almost a half turn. And by the time it's done, it's not pointing toward the sun at all. And if the sun were causing the highlight and the shadow on the moon, you would see the craters and everything move and the shadow would stay fixed and the highlight would also. Here are the two photos I took both in the same day. Look how much that's turned. And if you look at the craters, they've all gone right along with it. So that highlight and that shadow are not caused from the sun at all. Here's another set of photos that I took in December of 2018. And look how much that's rotated in the same day. This happens on a regular basis. It's quite an angle shift. I can see some of the craters on it, and they went right along with that highlight. This is my backyard, and I went ahead and put side by side where the sun sets and where the moon was setting on the day that I was drinking coffee, and noticed that the moon highlight was facing north and the sun had set in the southwest. Look at the angle of the highlight on that moon and explain somehow, if you can, how the sun is casting that highlight on that moon. I don't see how it's possible. Yeah, if you put the sun right down here to the right, that's where my wife thought it was setting. And I told her, no, it's setting down southwest. So let's play around. I'll put the sun right down where it should be. Now, doesn't that look a lot better? It could actually light that side of the moon. I can't see how, well, if the moon was transparent, the actual sun might be lighting that side, or it might be reflecting off the dome or something. Now I know people are going to come back and say, well, you don't know calculus or you don't know physics, you're a moron. Well, what kind of a moron would I be if I thought that actual sun was casting that highlight on that moon at that angle? I would have to be quite a moron. But it's not casting it, not at that angle, it's not. It's an easy thing to do to prove to yourself that the moon is rotating and the shadow and the highlight all simultaneously, just on a clear day, not at night. Take an early morning photograph, take one at around noon, and take one around evening, and you'll see that that's all of it's rotating. And then pay attention to where the craters and stuff are.
Care.
That's my job! That's what I do! I don't lose! I win! I win!
Is there no one on this planet to even challenge me?
Maybe you came by to congratulate me on last night's victory.
Hold in the center. Back to focus on the light point.